Okay, so let us continue our exercises. In this ninth one, we have to prove what we have mentioned a few times before, namely that if x is a subset of R, then any adherent point of x is either a limit point of x or an isolated point of x, but of course not at the same time. Conversely, every limit point and every isolated point of x is also its adherent point. So let's see how this can be established. So we will show this one first. That is, we will consider any adherent point of x and show that it's either a limit point or an isolated point. So let x be any element in the closure of x, or in other words, this small x is any adherent point of capital X. Now if for every positive real number epsilon, we have this intersection non-empty, okay, then by definition x is a limit point of capital X. Why though? That's because what does this intersection being non-empty mean? It means that there is at least one element in capital X other than small x whose distance from small x does not exceed epsilon. Okay, so and that is just simply the definition of a point being a limit point of some set. So if this happens, then our small x is a limit point of x. But what if this does not happen? This is not the case. Otherwise, there exists some special epsilon, some positive real number, epsilon 0, for which this does not happen. Such that this intersection is empty. Okay, now what? What can we say in this case? But at the same time, x also is an adherent point of x. So if we apply the definition of adherent points for this epsilon naught, we get another similar thing. Since x is in the closure of x, we also have this not equal to the empty set. Or in other words, in the language of inequalities, there will be at least one element in x which is close to small x in the sense that the distance between them is at most epsilon 0. And let z be such an element. Okay, now let us look at these two conditions. This interval does not intersect this set. However, at the same time, that same interval intersects x. So that means the intersection should happen exactly at this element small x, not anywhere else on the set x. Thus we have two things actually. One of them is this, that x itself must be this z, because this z is a point in this intersection, but from combining these two things we see that the intersection can happen at only x. So x becomes equal to z, but z already belongs to this intersection. That means in particular z is also an element of x, and this intersection is in fact this. Why I wrote this separately, you need not write, but it just simply emphasizes the fact that x is now an element of capital X as well, and at the same time this intersection is this singleton set. So by definition small x is an isolated point of capital X. Note that in general small x need not be an element of capital X, it just belongs to the closure of X. As an element in the closure, it may or may not belong to the set itself. So we have shown that any adherent point is either a limit point or an isolated point. Also, by definition, X cannot be both a limit point and an isolated point. Exactly why, that you go back to the definitions of these points, and you should be able to see from the definition itself that being a limit point as well as an isolated point is simply impossible. Okay, I am not going to elaborate on that. Another thing is that the converse easily follows from the definitions. Let me at least say something about this part, although I am not going to write anything here. So the solution in fact ends here. So what I want to say here is this. What is the converse? The converse asks us to show that every limit point is an every limit point is an adherent point, and also every isolated point is an adherent point. Okay, I am stammering, I don't know why. Let us first take the case of an isolated point. If x is an isolated point of capital X, then by definition x is also an element of capital X, and then some other condition is true, right? Now, being an element of capital X, x is automatically an adherent point, because we know that the closure of X contains X as a subset. What is the other thing? If X is a limit point, then you go to the condition of limit points. What does it say? It says that for every epsilon, the corresponding neighborhood of X intersects the set X from which small x itself has been removed. But after all, it intersects X somewhere. No. So by definition, it's an adherent point again. So that's why I said that converse easily follows from the definitions. Okay, so let us now see the next part. If X is a non-empty subset of R, show that X is bounded if and only if both the infimum of X and the supremum of X are finite. Okay, so let's see the solution. So here also we have to show two things, I mean both sides of a double implication. So let us first start by assuming that X is bounded, show that these two quantities are finite, and then we will go to the converse. Let X be bounded since X is already given to be non-empty. It means that X is a non-empty bounded set of some real numbers, or more specifically a non-empty bounded subset of R. So by the least upper bound property, the supremum of X is itself a real number, and least upper bound property means theorem 559. Then by theorem 559, the supremum of X is a real number, and in this regard let us just recall the actual definition of the supremum of X. If X is non-empty and has an upper bound, actually the entire set X need not be bounded. X just needs to have an upper bound so that the supremum of X is a real number. But being non-empty, if X does not have an upper bound, then the supremum by definition is plus infinity. However, if you start with the empty set itself, then its supremum by definition is minus infinity. Okay, so among all these three cases, we are in that case where we have a non-empty set that has an upper bound. Since X is non-empty and bounded, we also have infimum of X finite. Here also you can either think of the infimum as the greatest lower bound, what you know as greatest lower bound, you can apply that interpretation, or you can actually use the definition of infimum like this. Do you remember that in one of the exercises, this is how infimum has been defined? If your X is bounded from below, actually it's given that X is bounded, so that means x not only has an upper bound but a lower bound as well. If x is bounded from below, that is, if it has a lower bound, then minus x will have an upper bound, which will be the negative of that lower bound. So minus x then becomes a non-empty set because x is non-empty. And what is minus x? In minus x, you have the negatives of all the elements of x. So this then becomes a non-empty set which has an upper bound. So again, by our theorem 559, the supremum of minus x is a finite number, it's a real number. So its negative is also a real number, and that by definition is the infimum of x. Okay, so that's how we have one half of our claim. Conversely, let the supremum of x and the infimum of x be both real numbers, that is, they are both finite. Now let us consider this quantity. Let n, capital N, be the, I will not be able to write it fully here, but let me start here. Be the maximum of the absolute value of the supremum, and there are two other things within this maximum function. Then the absolute value of the infimum of x and 1. Okay, so it is something, it is the largest among these three numbers, and I say numbers because it's given that these two are finite, so their absolute values are also finite. Moreover, note that because we are considering non-negative real numbers and 1 is in fact positive, so n being the maximum of them is itself positive. Furthermore, this n will be greater than or equal to the absolute value of the supremum and also greater than or equal to the absolute value of the infimum, from which you will next get this as well. Then this and x is a subset of this closed interval minus n comma n. But then by definition x is bounded. The fact that this n leads to this containment is left to you to understand exactly why this happens. Okay, you go through the calculation yourself. But of course, if you don't get it, then let me know in the comment section below. So this is just the solution. Let us see what comes next. Nine 11. Show that if x is a bounded set in R, a bounded subset of R, then its closure x bar is also bounded. This one is rather easy. since X is bounded, so by definition X is contained in one such interval, for some positive n. But then, applying the various properties of closures of sets, we have this. One of those properties says that the closure of X is contained in the closure of this closed interval. But one of the results we already saw in this section says that the closure of the closed interval is the closed interval itself. In other words, any such closed interval is a closed set. But that's it. Then again, by definition, this is also bounded because the closure itself is now a subset of one such interval. Hence, this is bounded. And finally, let us see one more. Show that the union of any finite collection of bounded subsets of R is also a bounded subset of R. That means if you consider finitely many bounded subsets of R, no matter how many, it can be thousands, millions, billions, it does not matter. And if you take their union, then no matter how large the union is, it will still be a bounded subset. And is this conclusion still true if one takes an infinite collection of bounded subsets? That is, if the cardinality of the collection is changed from finite to infinite, then is the same thing true? It's not true. Is the same conclusion true, still true? Same thing if one takes infinite collection of bounded subsets of R, and I will give instead of a solution a hint. The solution is actually extremely easy, but often what you think is easy, and it is also easy. Conceptually, this type of things are quite easy. But when you try to write a formal solution, you may have to overcome some things, okay? Because in a formal solution, you have to, whatever you are writing, that should be clear and absolute and complete as far as possible. So the hint here is this: instead of straight away taking a finite collection of bounded subsets, you just first of all take two bounded subsets. Okay, so let x and y be two bounded subsets. That means x and y, each one of them is contained in some closed interval as a subset. Now for specificity, let me just simply take some concrete closed interval, say 1, 2, say x is contained in this, and say y is contained in 3, 4. Then what can you say about x union y? What can you say means you can of course simply, you find it somewhat difficult to say something, but you may find that x union y is contained in this interval. Now these intervals of course can change, their positions can change, their sizes can change, the endpoints may be negative, positive, many things can happen. And from among those many cases, you have to somehow come up with this and this. That is, regardless of what you have here, say here you have A and B, here you have C and D. You have to think of a number here which will be the left endpoint, say E, and a number that will be the right endpoint F, so that if x is a subset of closed interval a comma b and y is a subset of closed interval c comma d, then x union y will be a subset of the closed interval e comma f. And this should happen irrespective of what this a, b, c and d are. So you need to figure out what E is in terms of ABCD and what F is as well in terms of ABCD. So this part I leave to you. So once you prove this, you can then extend this result, this small result, by induction to any finite number of bounded subsets, and that will give you a positive answer to this first part. And the answer to this second part is negative, that if you consider bounded subsets fine, but infinitely many, then it's not necessary that their union has to be bounded. And one very easy example is just this. You consider this collection. N is a natural number, and the subsets are these closed intervals, all of which have 0 as their as their midpoint, and the left endpoint is -n, right endpoint is n. So these sets themselves by definition are all bounded subsets of R. In fact, they are in intervals, but their union, you will see, equals R, which itself is not bounded. So that shows that this second part in general is not true, means it's not true. Okay, we can't say anything about the boundedness of the union if there are infinitely many sets involved. So you try to do this part, you try to actually write the solution, a general solution which will not have such specific numbers. And with this I end the video for tonight. Our next upload is this coming Tuesday, and on Tuesday let us what shall we do? groups, fields. On Tuesday, let us go back to vector spaces. I think right now we are solving problems on inner product spaces, right? So on Tuesday, instead of having a regular video, we will have those community updates, okay, where I will post solutions. So see you on Tuesday with that. I'm signing off for tonight. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.